Section 3.4 starts off discussing linear and angular speed. We are again looking at application for radian measure. This video is going to take you into several word problems. We're going to try our best to deal with them. Hopefully it will not be too painful. Okay, in many situations we need to know how fast a point on a circular disc is moving or how fast the central angle is changing. I've given you a brief sketch of a circle here, and you can see that you have a point P here on your mark, and it's moving in that direction. Of course, as that swings out, then your angle theta is going to change. Remember, your arc length is still S, and you have your radius of R. And so all of this you've seen before when we talked about the old formula. We looked at arc length is equal to the radius times theta. And so we've talked about some of these measurements before. Suppose that P moves at a constant speed along a circle of radius R and the center 0. The measure of how fast the position of P is changing, and that is actually, the center is actually the letter O, but it's at 0, 0, it's at the origin. The measure of how fast the position of P is changing is called linear speed. Okay, linear speed is one of the things we're looking at. It's represented by the letter V. You might recall that just in a basic physics class, your velocity is typically equal to your distance divided by your time. Well, that's the case here. It's just that our distance is now represented by S, where S is the length of the arc traced by point P over time t. So nothing new there. Velocity is distance over time. That's a standard practice. And now our distance in reference to this would be the length of the arc. That would typically be given in centimeters or inches or feet or something of that nature. It's a distance. And time, of course, would be in seconds or minutes. So we should look for our velocity, linear velocity, to be in something like meters per second, or feet per hour, or something of that nature, inches per days, some kind of a length measurement associated with some sort of time measurement. Okay, as that point P moves along the circle, the ray OP obviously rotates around the origin, and the measure of this angle, POB, is going to change. The measure of how fast the angle changes is known as angular speed. Now, angular speed is symbolized by the Greek letter omega. The formula is similar to linear velocity, and we'll see these two connect very shortly. But the formula for omega, or angular speed, is theta over time. So now remember, theta can come to you in revolutions, and it can come to you in degrees, but what we need it in is radians. So sometimes you may be looking at an angular velocity if you look at revolutions per second, but you would need to change that to radians before you could use it. Okay, so now let's connect. We know from our section 3.2 that arc length is equal to radius times theta. And since velocity is equal to arc length divided by time, we could just simply replace this r times theta in this spot. So velocity is also equal to r times theta divided by time. But now notice theta divided by time is what we had for angular speed. So we could rewrite this formula here as r times omega there. And so I'm going to put those formulas together for you on the next page, so don't stress on me. Alright, angular speed. You have that theta over time, where theta is in radians, but remember sometimes it won't be given in radians and you'll have to get it there. So just a note, if theta is in revolutions or degrees, you'll need to take it to radians. Okay, and we'll see that as we work these actual problems. Now, linear speed has a multi ways of representation. We could do velocity as arc length over time. Remembering that arc length is the radius times theta, you could use radius times theta over time. And remembering that theta over time is angular speed, we could use radius times angular speed. So 3 different formulas for linear speed, and all through this you need to hold on to that one that we had for arc length. It's from the past, but you may need him. This was section, oh, not right in that close to the edge. This is section 3.2 if you're looking for where that is. Now, for the next several pages, I want to just take you through some word problems and see if we can't make all of this mesh. This chapter is bringing so many things together. Hopefully you're going to hang with me. Alright, couple of things as you work word problems. Number 1, identify what you're given. And number 2, identify what you want. And then work these formulas up here to get it together. Okay, so I have a point P on a circle with a radius of r. The ray is rotating with angular speed omega for the given values of r, omega, and t. So they're giving us these values. We want to find the following. So let's just see what we're given. The radius is this. Angular velocity is this. And then of course time is this. Radius and time are pretty standard. Omega is angular velocity. So the first thing I want to find is the angle generated by P in time t. I want to know what is theta. And remember, this ultimately needs to be in radians. Okay, so I'm looking at my formula. This one has theta in it and this one has theta in it. Well, I have omega, angular velocity, and I have time. It looks to me like I could use this angular speed without any problem for part A. Angular speed is theta over time. The angular speed that I've been given is pi over 12, and this is radians per second. Theta is what I'm looking for, and I want this over 6 seconds because that is my time. Now, if I wanted to solve this for theta, I would just multiply this side by 6 seconds and this side by 6 seconds. These are going to cancel. So I have theta. Notice these seconds cancel also. And then just simplifying, I would get 6, let me write that in black, sorry. I would get 6 pi over 12 radians. So actually, theta is just pi over 2 radians. We know that is 90 degrees. And the radians are not necessarily required. If you just told me that theta was equal to pi over 2, that would be great. Remember, radians are understood at this point, and if you mean degrees, you better put the symbol. So A part, we found our actual theta. Now B part asks you to find the distance traveled by P along the circle. Distance is going to be your arc length. Okay, so thinking about my formula for arc length, I know that arc length, back from what we've previously learned, is the radius times theta. Well, I just found theta, and I have the radius. So I'm going to use that formula for arc length. Arc length from of old is the radius times theta. I'm pulling back my knowledge from section 3.2. The radius is 20 centimeters. The angle theta in radians, and it always has to be, is pi over 2. So heading out this way, my arc length is going to be 10 pi centimeters, because I just divided the 2 into the 20. Right, the last part, part C, asks you to find linear speed. So linear speed, when I go back up here, linear speed is represented with the V, or we think about it as velocity. And I have a lot of different things. I have the arc length over time. Well, I have all of that. I have the radius and theta and time. I could use that one. Or I have the radius and this one. Now these two right here, I didn't do anything to find these. I have that piece of information to start with. So I think I'm going to use this last one just because it wouldn't be using any calculations that I made. So if I messed it up or made a mistake, that would be no problem. So my linear velocity is the radius times the angular velocity So the radius was 20 centimeters. The angular velocity was pi over 12 radians per second. And now that radians typically is not even written, so I'm going to reduce these by 2. Oh, sorry, I should have reduced those by 4. Forgive me. This was 20 and 12. So reducing by 4, that would give me 3 and 5. My velocity should be 5 pi over 3 centimeters per second. There is my linear velocity. And that takes us sort of through a scenario of the different things that could happen with linear, angular velocity, as well as arc length. Those formulas are all tied together. Alright, let's do more. These are word problems, and they function much the same as you're used to. A belt runs a pulley of radius 6 centimeters. So right there, radius of 6 centimeters, there's R. Alright, so R is 6 centimeters. At 80 revolutions per minute, now this is kind of tied in together. I'm seeing this as angle stuff. Revolutions deals with angles, and we're talking per minute. So this is either linear velocity or angular velocity, and since it's dealing with an angle, we're looking at omega. Okay. Remember, linear velocity would have different stuff. So what I have is my angular velocity is 80 revolutions per minute. Now be careful. Remember what I said about this. You need your angular velocity to be in radians. Okay, so I'm going to change this. I can do this. You know how to do this. 1 revolution, a complete romp around the circle, is 2 pi radians. So, what I have is my angular velocity is actually 160 pi radians per minute. Okay, so I just made this change so I would know I would be using the right stuff when I got ready to go. Okay, so first question, I've labeled everything out. First question asks me to find the angular speed or angular velocity in radians per second. I am almost there. So I'm going to take what I have. I have 160 pi radians per minute. And look guys, you can write the radians per minute like this, or you can write it like this. It just doesn't matter. Know that the radians per minute are on bottom. And I need to go to radians per second. So 1 minute is equal to 60 seconds. I put the minutes on top so that they would cancel. Which means now, if I reduce that, that would be 8 pi over, let's see, 2, 3 radians per second. That would be my angular speed in radians per second, just like they asked for. Okay. Now, the second part asks you to find linear speed. That's V. And they want it in centimeters per second. So, I have the radius. I have the angular speed. What I know for part B is that linear speed is radius times angular speed. Hopefully you will learn to memorize those formulas soon. My radius is 6 centimeters. My angular velocity, my angular velocity is 8 pi over 3 radians per second. And remember, we write this radians when we need it, and when we don't stress about it. So I wanted my linear speed in centimeters per second. I am there. I just need to clean this up. 3 goes into here twice. No, excuse me. 3 goes into here once. 3 goes into here twice. And my linear velocity is 16 pi centimeters per second. Notice the centimeters for your linear velocity is a length unit over a time. And that radians is just understood. Okay, so problem number 4 Still having you do angular and linear velocity without too much trouble. Problem, page number 5, problem number 3, or 4, whatever number we're on. You have a satellite traveling in a circular orbit 1,600 kilometers above the surface of the Earth. It takes 2 hours to make one orbit. The radius of the Earth is approximately 6,400 kilometers. And so they've drawn you a picture. Hooray. What you need to realize looking at this is that your radius for this whole deal is this whole distance. So right off the bat, your radius is going to be the 1,600 kilometers plus the 6,400 kilometers. So the radius we're working for is 8,000 kilometers. We need to hold on to him. We just added the two radiuses, the two distances together to give us the radius from the center of the Earth all the way out to that satellite in orbit. So that is what this information and this information handed us. Now we have another piece of information. We have 2 hours to make an orbit. Okay. 2 hours is obviously time. But more than that, I think you're going to need to connect this whole 2 hours to make one orbit. An orbit is the same thing as one revolution. In this case, if you started here and went all the way around, what you would know is that your theta would be 2 pi. Sorry, I can't read that. What you would also know is one revolution is 2 pi radians, and that would be equivalent to your theta in this case. So when they want linear speed is v. It looks to me like I could use, I have a couple of options. It's either r times omega, or it's s over t, or it's r theta over t. Of all of these, it looks like this is the one that I have the data for. So on A part, my linear speed is going to be my radius, which is 8,000 kilometers, times my theta, which I know is 2 pi radians, and the radians is not always necessary, divided by time, which is 2 hours. So velocity in this case, these 2's will cancel. Be careful not to pick up this. This will be 8,000, don't lose your pi kilometers, and since it's linear velocity, I don't need to work on my radians right now. They're there, but they're not important. Kilometers per hour. There it is. There is my linear speed. I wrote down what I had and which formula plugged all that together, and I went from there. Alright, part B asks you to approximate the distance the satellite travels in 4.5 hours. So I have a new time. I've got 4.5 hours, and I want the distance it travels. The distance, like if it started here and it ended here, the distance it travels, can you see that that's arc length? So, arc length is given by, and let me think, there's a lot of ways to think of it. Normally it's r times theta. When theta is in radians, but I don't know the theta. Why do I not know the theta, guys? Alright. I know that 2 hours makes one orbit, but I don't know that I'm making more than one orbit. So I just don't know what theta is. I've gone more than 2 pi at this point because I'm making more than one orbit. So I don't have that. So let's see what else I know. Oh, I know this. This may be the key. I know that velocity is arc length over time. I have the appropriate time with this situation, and I currently know what my velocity is. So I'm using a little bit of information that I've already calculated, but that's not a big deal. If you can avoid it, good. If you can't, don't kill yourself. Alright, so this is 8,000 pi kilometers per hour is equal to what I'm looking for, my arc length, over my time, which is 4.5 hours. If I want to solve this for S, I just need to multiply this side by 4.5 hours and this side by 4.5 hours. Those hours cancel, and my arc length is going to be, hey, I brought a calculator today, 4.5 times 8,000 would be 36,000 pi kilometers. Yeah, give or take an inch or so, right? And so that would be what my arc length would be that it traveled in 4.5 hours. How you holding up? One more. We're going to make it. Alright, the tires of a bicycle have a radius of 13 inches. Alright, so there's my R. They are turning at a rate of 250 revolutions per minute. I hope you see that as angular velocity, though we need to switch it to radians. And we want to know how fast is the bicycle traveling in miles per hour. That is linear velocity if I have ever seen it. So, it looks like I have everything for velocity because I know that velocity linear is equal to r times omega, which is my angular velocity. I just got to work on omega. R is 13 inches. Right now they gave me my angular velocity in revolutions per minute, but I need mine in radians. So one revolution is 2 pi radians. We're just making a quick conversion. 215 times 2. Everybody yell 430. Okay. Radians per pi radians per minute. Alright, so I just made a quick modification to my angular velocity, and now I'm going to use it. Velocity is the radius times the angular speed. I want to be in miles per hour. Y'all can't even read that. Clean that up. I want to be in miles per hour. I am not there. So, let's go ahead and just simplify this first. 430 times 13 is going to give me, I'm just multiplying these two numbers together, it's going to give me 5,590 pi. Right now I'm in inches per minute. The radians are not too purposeful. Alright, well everybody knows that there are 12 inches in 1 foot. Boom, boom. And you can use this conversion. There are 5,280 feet in 1 mile. And now I want to go from minutes to hours. So there are 60. This is cramming up over here. My apologies. This is 60 minutes in 1 hour. Oh, guys, it's not going to work over here for me. Okay, let's just go with it for a minute. Let's clean this much up. Or look, we'll just rewrite it. I've got 5,590 pi inches per minute. I'm rewriting this. Y'all hang with me. I know that 1 foot is 12 inches. These cancel. I know that there are 5,280 feet in 1 mile. The feet cancel. And then I know there are 60 minutes in 1 hour. The minutes go. So now I'm in miles per hour. I just need to calculate that. This is linear velocity. Alright, 5,590 divided by 12 divided by 5,280 times 60 times the illustrious pi button gives me an approximate velocity of 16.6 miles per hour. That little bicycle is traveling dirt slow. Not bad for a bicycle. 16.6 miles per hour for that bicycle. And that, guys, was a long video. Oh, I have one more. Oh, can y'all take it? Let's do one more. I want to make sure you have plenty of examples to survive. All right, pulley has a radius 12.96 centimeters. Suppose it takes 8 seconds for 56 centimeters of belt to go around the pulley. Here's your time. Here's your radius. This 56 centimeters of belt going around the pulley, that is arc length. So we want to find, first of all, linear speed. Linear speed, that's easy. Arc length over time, we can do that. Arc length, 56 centimeters over the time, 18 seconds. And my arc length is going to be 3.1111, you get the idea, centimeters per second. Part B, angular speed in radians per second. Well, part B, angular speed, is typically, let's see, let me start over. This is what I do know. I know that linear speed is r times angular speed, and I'm looking for the sky, but I have this one and I have this. I can fill this in. This I'm going to rewrite as 56 over 18. These are centimeters per second. We'll see how our units come out. The radius is 12.96 centimeters, and I would really like to find angular speed. So I could divide this by 12.96 centimeters as long as I divided this by 12.96 centimeters. Okay, the centimeters cancel, and so these cancel. Omega is going to be left. I've got 56 divided by 12.96 divided by 18. Anything on the bottom you hit divided by. Anything on the top you hit times. So that's 0.24. That's a decimal. 0.24005. This is angular velocity. Those radians are floating out there. These are radians per second. So I picked up radians when I needed them. We're going to survive. We're going to make it. Let me check my answer. I got these out of your book just to see how everything was going. Yes. Good. Questions about these? We will talk about this again on Monday. Why does that not look? Hold on. Let me find this one. I do want to double check it. I don't even know where I got this problem. Oh, okay. 39. Yes, it is correct. Okay. We will talk about more of this stuff on Monday, but guys, that's going to pretty much wrap us up for this. Looking to test on Wednesday. So you come Monday with questions, and we're going to survive. All right. Good.